So welcome to our first lecture for Research Methods 2. It is on the normal curve or the bell curve. During this lecture, I want you to learn that number one, the normal curve or bell curve is a curve of chance. Two, that if you place this curve around an experimental result and take the middle 95% of this normal curve, you get a great estimate of the population result. Population results are the purpose of science. For example, we want to estimate how therapies impact all humans, not just the Regis students in our sample. Number three, I want you to learn that if we place the curve around the hypothetical null hypothesis, which I will describe later, we get the curve that is used to find p-value. Number four, I want you to be able to explain why the p-value is a simple fractions problem. And number five, I want you to set up what I call a baby version of the normal curve as a proof of concept that will allow you to better understand what a p-value is. We live in a world of chance. There's an 85% chance of rain today, meaning there's a 15% chance of beach today. Ken? There's a 1 in 1 million chance of winning the Powerball, meaning there's a 999,999 chance of not winning the Powerball. Quantifying chance is just helpful to live life, to make better decisions, and is essential to science. I think it's important to point out that our understanding of chance is driven by logic and reason first, and that's what my students don't get. Chance is an idea. It's not a math equation. Chance is not necessarily data collection and trial and error, or, as I said a second ago, math equations. To understand statistics, you have to actually forget the equations. They came last. They are the solution to a philosophical thought problem. Today, I lead you through a few thought problems of chance that I think you will find helpful in your career as a psychologist. What is your chance of rolling a 6 on a dice? That one's easy. We can see there are 6 potential outcomes of any dice roll, a 1, 2, 3, 4, 5, or 6, and only one way to get a 6. So my chance of rolling a 6 on any given dice roll is 1 out of 6. If we actually do the math, 1 divided by 6 is 0.16. Repeating, of course, but we'll leave that there. We've calculated the probability of rolling a 6 on a single dice roll. The chance of rolling a 6 on a dice roll is 1 out of 6, or 0.16, or 16%, which is a probability of 0.16. So probability and percentage are interchangeable. Percentage divided by 100 is probability. Probability times 100 is percentage. They're interchangeable. However, this idea of chance isn't based on experimentation or even a mathematical equation. It's based on my thoughts. Specifically, I assume every side of the die has an equal chance of being rolled. This is mostly a true assumption, but every die is going to be a little different. Some may favor 1s by 0.01%. Some may favor 2s by 2.2%. I bring this up because the math 1 over 6 is not infallible. It's driven by my ideas of chance, my logic, my philosophy. Now, my ideas of chance aren't illogical. They aren't nonsensical. It's pretty fair to assume that all 6 sides of a die have equal probability of rolling. This assumption is probably the fairest in Vegas, where they actually measure the weights of the die and make sure they are balanced. Let's move away from the example of gambling. Let's say I'm a psychologist and I'm interested in the vocalizations of frogs, as I believe they help to express emotion. Now, science has to start with basic data collection. I order 100 frogs, 50 male frogs and 50 female frogs from my local PetSmart. I pinch each one of their butts and measure how loud their ribbit is. Why would I do this? Well, first, I know that all frogs are unique. There's Kermit number 1, who's different from Kermit number 2, who is different from Tadpole Sitter. I also know frogs are the same. That is, they have the same organs and same basic machinery for vocalization. I know some frogs are going to be born different and may not have the ability to make sounds because something that happened to them when they were tadpoles. I know other frogs are going to be born with an enhanced ability to make sounds due to slight variations in the developmental process that created bigger lungs or oddly shaped voice boxes. So deep down, I know 2 things. Frogs will have roughly the same loudness, And there are individual differences that make some frogs different than others. Now, to put this in the words of chance, I know that most frogs will relatively have the same loudness, but chance differences make some frogs louder or quieter than others. But how do I quantify chance? Now, to enter my class, you must have completed the entry ticket. Today's entry ticket is a few questions that you must answer while attending to this lecture. That's because I assume you're doing your homework when I design class. To be blunt, an underprepared student is not only dead weight in the class, holding back students who's prepared, but they also won't get anything from class because I designed it with the idea that you were prepared and had some exposure to the material. So with this entry ticket idea, if you don't have it completed, I'm actually not allowing you in my class if you don't have your entry ticket. But if you didn't prepare for class, I still want you to come to class and watch the lecture during class while we're doing fun activities, particularly games and stuff that help us learn. So essentially, you need to do these entry tickets every day when there's a lecture to get into my class. If you don't, you should still come to my class and do the entry ticket. And if you get the entry ticket done, by the end of the day, I'll give you credit for the entry ticket, but you will lose attendance points. I will check entry tickets every day. And for this one, I would just prefer if you use pencil and paper and you can bring in loose leaf sheets, whatever, it's no big deal. I want you to draw it on paper. So back to the lecture. Deep down, I know two things. Frogs will be relatively the same loudness, and there are individual differences that make some frogs different than others. Now, to put this in words of chance, I know that most frogs will have relatively the same loudness, but chance differences make some frogs louder or quieter than others. On a scale where your decibel reader only has seven outputs, extremely quiet for a frog, quiet for a frog, kind of quiet for a frog, average for a frog, kind of loud for a frog, loud for a frog, and extremely loud for a frog, I need you to make a logical guess as to how loud you expect your 100 frogs to be after you pinch them. Specifically, place each of your 100 frogs in one of the bins like this. Oh, this frog is loud for a frog. I'm putting him here. Pinch, right? I'm guessing. I'm just making this up. You don't have to actually pinch frogs. This one is kind of quiet for a frog. And this one is kind of loud for a frog. Now, I need you to finish this out, right? I started the problem for you. Finish this out. These are just guesses based on our logic. This is presented on the left, right? You can see the logic on the left. On a piece of paper, I need you to create your own graph like this. It's technically called a histogram, but represent each frog with a frog drawing on your graph and stack frogs on top of each other. Now, I need you to stop the video and complete the task. It's okay if you get the problem wrong. It's not okay if you copy my answer exactly. Now, what you see here is my answer. This is a curve of chance straddled around the truth. The truth is most frogs are about the average loudness for a frog. That's why I made the scale. So our truth is that our frogs are of average loudness, but individual differences, aka chance, some call it error, cause some frogs to be louder and quieter than others. So the normal curve represents truth, that most frogs are average loudness for a frog, but chance causes some frogs to be quieter or louder. Now this idea is the bell curve, which is also called the normal curve. A version of it is sometimes called the t-distribution. Now, if you were not allowed to have negative values, like if the lowest value you could have would be average for a frog, right? You would have to fold the curve over and you would get what we call the F distribution. Sometimes we call these types of curves Gaussian curves. These curves have many mathematical formulas, but they came from this basic idea, right? The idea for this curve is that most frogs are the same loudness, but chance, specifically individual differences like larger lungs and narrower voice boxes, causes individual frogs to vary from the center of truth, right? So if you get that there's a center, which represents truth, and a spread that represents an error, you get the normal curve. Now, the mean of all frog loudness equals our best guess at the center of truth. And that mean is going to be the average right there, like that average mark that you see right there. Average for a frog, if you averaged all these together and put this on a 1, 2, 3, 4, 5, 6, 7 scale, our average would be essentially 4. The mean is simple and needs no further explanation, right? But the standard deviation, how much these scores differ from that mean on average, is our best guess at error or deviation from the truth in the frogs themselves. It's our best estimate of chance or error. But, honestly, mean is self-explanatory, but the standard deviation formula needs a little bit more explanation. Now, let me show you 5 numbers. They're very simple. 1, 2, 3, 4, and 5. They sum to 15, and when you divide by 5, you get the average is 3. So the mean of this data set is 3. And we want to quantify the error in this simple data set. We really want to quantify the average difference from the mean as an estimate of error. That's our goal. So essentially, if we could say on average scores deviate from the mean by 4 units, we're saying that there are 4 units of error in our data set. So I need to, that was just like me talking. So now let's actually try to calculate the average difference from the mean. So I need to start by calculating difference scores. The score minus the mean. 1 minus 3 is negative 2. 2 minus 3 is negative 1. 3 minus 3 is 0. 4 minus 3 equals 1. And 5 minus 3 equals 2. So now to find the average difference from the mean, I have to find the average of these difference scores. But before I do that, I just want to estimate what I think the answer should be. I see that 2 scores are 2 units different from the mean. 2 scores are 1 unit different from the mean, and 1 score is 0 units different from the mean. So 4 plus 2 plus 6 divided by 5 equal 4 plus 2 plus 0 equals 6 divided by 5, which is an answer that should be slightly greater than 1. So that's just me estimating what I think the average deviation from the mean should be. But we can't just estimate with math. We have to actually calculate it. So to find the average, I have to add up all the scores. Negative 2 plus negative 1 plus 0 plus 1 plus 2, that equals 0. Then I have to divide by n, the total number of scores. There are 5. 0 divided by 5 is 0. So on average, my scores differ from the mean by 0 units. That's not right. That would mean all my scores are the same. So what's going wonky here? That's your second entry ticket problem. Entry ticket problem number 2 is what's going wonky here. Why did Dr. D get a 0 average deviation from the mean? What's wrong here? What is causing the average to be 0 when we know it should be a little bit greater than 1? Pause the video now. All right, I'm assuming you've answered the question. If not, I'm going to give you the answer, and that's fine. But it's really important that you think about these things. The reason why we got the average deviation of 0 is that the negatives and positives cancel each other out. And the average deviation from the mean will always do this. So I know what you're going to say. Just take the absolute value. That makes the most sense. And you're right. It sure does make the most sense. But that's not what we do. We first square each difference score to get rid of the negative values. Then we sum the square difference scores. This is all sum of squares is the sum of the square difference scores. Then we take the average of the square difference scores. So on average, scores differ from the mean by blank squared units, which is called variance. Then we get the square root to find the standard deviation, which is essentially saying that on average, scores differ from the mean by 1.4 units, which is close to what I estimated earlier. So let me show you that. Like, we square the difference scores. 2 squared is 4, 1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. We add these together to get 10. That is your sum of the square difference scores, right? We divide these, we get the average of these. We divide by n, let's say 5, right? So 10 divided by 5 is 2, and that is called your variance. We take the square root of variance, getting 1.4, which is a little bit larger than 1. It meets my estimation from earlier. It's not perfect, but it's close, and that is our standard deviation. Now, in reality, when we find variance, we divide by n minus 1. So we wouldn't divide by 5, we divide by 4. I don't care if you know how to do this by hand. I don't care if you do this by hand. We use a stats program that's our stats nerd buddy and can do these calculations perfectly. But I'll tell you why we do these weird adjustments and these weird calculations. When we calculate the standard deviation this way, our data better estimate the population effect we're seeking. In this case, the loudness of all frogs of the specific variety, bullfrogs, on the entire planet. See, when you can estimate population data, you're doing something you could never do in real life. Collect data on every member of a population. In this experiment, it's all bullfrogs. In our daily work, it's estimating how things work for all humans. Oftentimes, when we do something weird in statistics, like calculate the standard deviation instead of the absolute deviation, it's because it provides a better estimate of the population effect. That's why we don't use the absolute deviation. So for us, if we measured the depression of humans at Regis and calculated the absolute deviation, our estimate of error, our data would only be applicable to Regis students in our study, not humans in the world, not the population we're interested in. If we calculated the standard deviation, our data would be applicable to all humans in the world, or maybe just all humans in America, which is still really cool. But the point here is that by using the standard deviation and not the absolute deviation, we can draw conclusions about population of humans that were not in the study. As psychologists, we run experiments to try to help all humans, so we use these weird statistics like standard deviation instead of absolute deviation so we can draw those conclusions. Now, I totally got off track. The normal curve represents truth plus chance. The mean represents truth, the middle of the normal curve. The standard deviation represents chance, how much scores differ from the mean, which is the spread of the normal curve. The spread of the normal curve represents error. All right, so this curve is my original normal curve that I drew. Let's just say, for the sake of argument, the standard deviation is 1. It's quite peaked. Now, what would happen if my standard deviation was 5? Right? That means there's more error in my estimate of truth. And what would happen is that this curve would get flatter and flatter, get less peaked. Let's look at an example of that. You can see here that my curve itself, it went from a nice peaked normal curve to more of a flatter curve. Curves like this have more error in it. More peaked curves provide better estimates of the truth you're seeking. Now, entry-level ticket question number 3 is pretty simple. Draw 2 normal curves, one with a very small standard deviation and one with a very large standard deviation. Now, we're going to move on to using the curve of chance in experiments. Before, we were using the curve to predict basic measurements of 100 frogs. That is not what we do in science. In science, we run experiments on groups of frogs, essentially. I have some evolutionary psych friends, and they told me that cries of female frogs should be louder than the cries of male frogs to protect the babies. Like it will call in the force of the battletoads to protect the babies or something. I said to them, interesting hypothesis. I have frogs. Let's mess around and find out. So I categorized my male frogs and female frogs into different groups and calculated the mean difference on my 7-point scale of loudness. Right? I found a 1-point mean difference between female frogs and male frogs. And based on the pattern in the means, they appear to be right. Female frogs are louder, higher decibels than male frogs. But I'm not accounting for chance at all in this estimate. Is their hypothesis right? Currently, the pattern of the data suggests they were right, but we haven't accounted for error. You can see that we're going to have another entry ticket question number 4. You can see it on the screen, but I'm going to kind of give it a little bit of setup here. Now, if I assume that my experimental result represents truth, which is not a bad assumption, I ran one experiment. This experiment represents my best guess at the average sex difference in frog loudness. However, I realize that there's no way that 1 is the exact average sex difference in frog loudness. There's error in all experiments. So I need to add my error curve to my experimental result to get a better estimate of the result in the population, because that's the goal of science. Essentially, I need to plop a normal curve on top of my experimental result, centered at my experimental result, to get a better estimate or prediction of what the experimental result would be in the population. Now, if you're looking at the scale, you see it goes from -6 to +6. You're like, how did I get that? Well, I labeled each of the points, extremely quiet for a frog, that's 1, right? Quiet for a frog, that's 2. Kind of quiet for a frog, that's 3. Average for a frog is 4. Kind of loud for a frog is 5. Extremely loud for a frog is 6. Or like loud for a frog is 6 and extremely loud for a frog was 7, right? But when I start a problem like this, I ask myself, because it's an experimental result. It's not measuring the frog anymore. It's what is the largest experimental result I can get. And in this case, we're talking about mean differences, where we're going to take the loudness, the average loudness for female frogs minus the average loudness for male frogs, right? So the largest difference I can get is that female frogs, all 50 female frogs are extremely loud. They all get 7s. The average of all 7s is 7, right? And then for the largest experimental result I could find, right, in the direction we predicted, all the male frogs would be extremely quiet for frogs. They all get 1s. The average of 50 1s is 1. So you get 7 minus 1 is 6. That is the largest result we can get. Now, if the result was in the opposite direction, we were wrong and male frogs were louder than female frogs, right? Well, we'd still do the math the same way. Female frogs minus male frogs. But in this case, female frogs would be 1 and male frogs would be 7. So -6. That's where the bottom comes from, okay? Those are all the possible experimental results using the scale we used, right? So, that sets the scale. And also for this problem, if we just rounded every result that you're imagining to a whole number. So if you're like, oh, I think the result would be a mean difference of 4.54. Round it up to 5, okay? If you do that, everything will work. Now, in an ideal world, we would run every experiment 100 times and build this curve from actual data. However, we don't do this because that would waste billions of dollars and would really stop scientific progress. If you think about that, for everything you had to run it 100 times. So all we do is we ran one experiment and found a mean difference of 1 where female frogs were louder than male frogs. We know chance exists, so now we want to plop a normal curve on our result. Now I want you to use logic. Assume the population result is 1, where female frogs are louder than male frogs by 1 unit. And you ran this experiment 100 times. What experimental results do you think you would obtain? This is entry ticket problem number 4. Now, instead of a frog, because before I was measuring the loudness of individual frogs, I'm using this symbol of the atom to represent a single experimental result. This will highlight that this curve is a curve of 100 experimental results, not 100 frog loudnesses. But I want you to complete this entry ticket problem. As it is stated, essentially plop down your normal curve. Statisticians have shown and proven that the population truth, the population result of this experiment, the population sex difference on frogs in this example, is likely to be in the middle 95% of this distribution. So 95% of the time, the population truth is within the middle 95% of a normal curve plopped on top of your experimental result. This middle 95% of the normal curve is called the 95% confidence interval. Clearly, this is just a proof of concept. And with this specific 95% confidence interval, the population sex difference could be anything between male frogs are 2 points louder than female frogs, or female frogs are 4 points louder than male frogs. If you look, I got that middle 95 result. The middle 95, it includes 2 and 4, -2 and 4, and everything in between. So the population result could be that male frogs are louder than female frogs by 2 units. Male frogs are louder than female frogs by 1 unit. Male and female frogs are the same loudness. Female frogs are louder by 1 unit, 2 units, 3 units, or 4. All of those are possible population results. So I'm saying, hey, with this experiment, my experiment kind of sucks. I can't even tell you if male or female frogs are louder. Now, the 95% confidence interval estimates what the experimental result would be in your population. All you do is run one experiment, plop a normal curve on it, and take the middle 95%. This gives you the estimate of the of the population result, the result in the population, or in this case, the population sex difference on frogs. Now, with the previous example, that result didn't tell me much. Male frogs could be louder than female frogs could be louder than male frogs. All I know there is I need to run a better experiment, and that's fine. We did not make a scientific discovery with that data, but this is how a 95% confidence interval works. Now imagine I ran the same study, but I ran it better. I used 1,000 frogs, and I got a much tighter standard deviation. Now, if you look at the bottom here, my scale doesn't go all the way from -6 to +6. It could, right? It could go all the way out there. But with this example, I didn't need all the bins. What happened was that my standard deviation got tighter and tighter and tighter. And when that happens, right, I found the same experimental result of mean difference of 1, and I found the middle 95%. And what I find in this specific example is that definitely female frogs are louder than male frogs. I made a scientific discovery. So when you run a better experiment, you can, draw conclusions. Now, the previous example, we didn't make a scientific discovery. We didn't know if male frogs or female frogs were louder. Now, if this were our data, we would know that female frogs are louder. Furthermore, the standard deviation of loudness in this second study, let's say it was 0.1, this would tell us that female frogs are between 5 and 15 standard deviations louder than male frogs. And that would be a massive result. But I'm just showing you how we can use the 95% confidence interval to claim a discovery. Essentially, if my 95% confidence interval doesn't include 0, I know that female frogs are louder than male frogs. And then I can think about standard deviation and say, wait, these female frogs are 5 standard deviations to 15 standard deviations louder than male frogs. Now imagine if you were 5 standard deviations smarter than your peers. You'd be one of the smartest individuals, one of the smartest college students in the entire United States. And if you were 15 standard deviations smarter than your peers, you would be building time machines. But this is just an example to show you how we can use the 95% confidence interval to make a prediction about the population's effect and claim whether or not you made a discovery. With this data right here, I am fairly confident in claiming that female frogs are louder than male frogs by quite a bit. Now, p-value uses a very similar idea. Essentially, you plop a normal curve on top of the null hypothesis. The null hypothesis is the hypothesis of no effect in the population. So for this example, it's the hypothesis of no sex differences in the population itself. So entry ticket number 5 is just I need you to define the null hypothesis. What is a null hypothesis? Pause. Now we're back. Entry number 6 is draw the normal curve used to find p-value. Let's say, you need to understand this, I ran 100 experiments, so it's going to be like the last one. I'm going to have 100 experimental results. I'm going to represent mine with that sign of the atom to show it's an experimental result. There was no sex difference in loudness, in frog loudness, but I do know that chance impacts my results. So I want you to go ahead and draw the normal curve where you assume the null hypothesis is true, you ran 100 experiments, and chance impacts your results. Here's my answer. You notice it's a bell curve that is centered around 0. 0 is the null hypothesis being true, right? Positive results, female frogs are louder than males. Negative results, male frogs are louder than females. Your result doesn't have to be exactly like this, but if it looks like this, you're getting the idea. Now, don't forget, we ran one experiment and found a mean difference of 1. We now need to use this mean difference to try to figure out our p-value. I like to play around with this experimental result of 1 and figure out what probabilities I can find from it. That is, I like to take the mentality of the first statisticians, right, that didn't know what a p-value was, but were inventing it. So first, what can I find? I can find the probability of sampling a mean difference of exactly 1 if the null were true and chance existed. It is technically the area of this line. Lines have no area, so that probability is 0.000. However, the probability of sampling A mean difference of exactly 0 is also 0.000. The probability of sampling any mean difference, -6, 5, whatever, is 0.000. So this is not p-value. This is likely the snag the first statisticians hit as well. This tells us nothing. This is useless. One way to bypass this issue in the previous slide is I can find the probability of sampling a mean difference of 1 or greater. Now, why would I do this? Well, if we ran an experiment and found a mean difference of +2, this is a great result for a 6 difference hypothesis. 3 even better, 4, 5, 6, and so forth. So since the probability of sampling our exact result is always 0, we can find the probability of sampling results as good or better than ours. Now, I'm going to state this slowly. The p-value in this example is the probability that we would sample results that are equal to or stronger than the results we found in our experiment if the null were true and there were no difference in the population. Try to write this down. The p-value on this slide is the probability that we would sample results that are equal to or stronger than the results we found in our experiment if the null were true and there were no difference in the population. This tells me the probability of sampling results has or more extreme than my experimental result if the null were true and if chance existed. Now that probability is all of these experimental results. We add those up and divide by 100. That would be the p-value for this specific study. Now this is one acceptable way to calculate the p-value. It's called a one-tailed p-value, but it's not the best way. It's not the way that you get to use. Essentially, I don't want you to think about it too much, but we also have to calculate the probability of sampling a mean difference of -1 or more negative. You're probably asking why, and it is to give your work the best chance of being published, you have to use two-tailed p-values. Essentially, you're looking at it, you found a mean difference of 1, right? More stronger results include mean differences of 2, +2, 3, 4, 5, and 6, but also -1, -2, -3, -4, -5, -6, right? So essentially you have to use a two-tailed p-value. So that's just truth. So your p-value would be all of these results divided, the sum of those divided by 100. It's just a simple fractions problem. So what is a p-value? First, it comes from this graph that assumes the null is true and that chance exists. Right? It assumes the null is true. Look at the most common sampled experimental result. It's assuming 0 is the true experimental result. It is specifically the probability of getting a result that is equal to or more extreme in any direction than the result of your experiment if the null were true, if we assume the null were true and chance existed. So the probability of getting a result that is equal to or more extreme in any direction than the result of your experiment if the null were true and chance existed is your p-value. You need to write that down and understand that. So you need to memorize this. The p-value is the probability of getting a result that is equal to or more extreme in any direction than the result of your experiment by chance if the null hypothesis were true. I need you to know that the p-value is simply a fractions problem. Let me illustrate. Imagine Michelangelo ordered a bell-shaped pizza because Ninja Turtles love pizza. You have to see this pizza as one whole pizza. There it is. It has a very large standard deviation, so it's flat, not peaked. Right? Donatello, the scientist, got the pizza and asked Michelangelo, the meathead, if he wanted to eat a significant amount of pizza. Michelangelo, or Mike as we call him, said yes, so Donatello cut him 2 pieces. Donatello said, enjoy your pizza, it's significant at p equals 0.02. So Michelangelo only got 2% of the pizza. P less than 0.05 is significant, but I'm not going to tell you why. Right? This is your final entry ticket. problem, entry ticket problem number 6. Your final job for your entry ticket is to think and then answer this question. What do we know when our p-value is less than 0.05? And why is this knowledge a valid way to claim we made a scientific discovery? That is, your last problem is to become the statistician, the first statistician, and tell me why we use p less than 0.05 to claim that we made a scientific discovery. Give it your best shot. It's okay if you miss it, but give it a shot.